Hello, Vish. Hello, Arvin.
It's
Hello, Will.
Hello.
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 Yeah, hello.
Yeah.
Good morning.
Good morning.
So, do we just need to finish this PPT, the second half from Half-Life,
Yeah, pretty much.
pretty much?
yeah, pretty much, yeah.
Okay. What else have you guys been doing at school?
I think we did like a beer experiment
Mm-hmm.
at school, looking at the half-life,
Mm-hmm.
how what disintegrates
Yeah.
over time. So yeah, pretty
And
much.
when is that one due?
Oh, no,
No,
that
it's
was
just
just like an in-class.
Yeah, we used to every 2 weeks we do one like practical over
Mhm.
a double period. And
So is that beer experiment worth anything?
no,
No, not really.
it's just a class.
Okay. So it's finished, is it?
Mm-hmm.
yeah.
Did you guys work out the half-life for the beer foam?
Yeah.
Yeah.
Okay. Right.
We got
apparently it's like if you something like if you graph natural log of 2 against something gives the gradient gives you
Yeah.
something like, I don't really understand that bit.
Okay. So I think probably what you guys did is just give me a second. Yeah, so probably what you guys did is this is like the volume of the form, and this is time, and it could go like this, you know?
Yeah, something like that.
And then if you do the natural log of V versus time,
yeah. I think this is what we did in class.
then you get some gradient like this. You figure out the gradient.
Mhm.
That's lambda.
So because if you have a n equals to n naught e to power of negative kt, and if you take the natural log of n, and you get this one as a natural log of n naught plus minus kt natural log of e, which becomes 0. So this point here is basically the natural log of n naught, and the gradient here is the k value, the negative k.
Yeah, well, I have a question. What is this natural log like? Like what is that?
Natural log.
E.
Yeah, what is this natural log? Why are we using the normal log?
Okay, so you can use any log you like. You can use log base 10, but the natural log is the log base e, and e
Okay.
is a constant, a 2.7182818, something like that.
Yep.
So because we have this e, that's why we take the natural log. Then we can easily get rid of this guy, right? Yeah. So the number. So do you guys know how to go from here to here?
Not really.
Not really. Okay. So there's a log rule. When you have log of x times by y.
Yep.
then this is a log of x plus log of y. Do you understand?
Yeah.
When you have log of x over y, this is equal to log of x minus log of y. Is that right?
Yep.
When you also have log of x to the power of y, then this y comes down to the front. So y log of x.
Okay.
Finally, if you have log, so let's say this is a log base c. Okay?
Yep.
And if you have log base cc, you get 1. Understand?
Yep.
So these are all the log rules. I mean, most of them. So have a look.
Yeah, we've done this before, yeah.
Yeah, so if I take, so let me first talk about this equation here. This one here. This one here says, and you can also write this one as n is the number of remaining particles. N naught is the original number of particles. And you can have base half to the power of n, where n is known as the number of half-lives. So you can do it like that. So for example, if original amount is 100, and
I think we've already done this these two equations.
yeah, you already know these equations, right? Can I skip this one? So what I'm trying to show is if you take the natural log of n on this side and natural log of n naught e minus kt, then first this breaks into natural log of n naught plus natural log of e minus kt, right? Using which rule? The first one here, right?
And then e cancel that.
And then this one comes down to the front, and then the natural log of and e cancel out because that's like log cc, you know?
Yep.
This becomes ln n naught minus kt, and you get the ln n.
Oh, okay.
Then you get sort of a straight line. Did you get a straight line for beer?
Yeah.
Yeah.
That's excellent. So because that means beer obeys the exponential decay rule. Not all of the natural phenomena obey the exponential decay. Now, so once you figure out the gradient from this straight line, this is so you see this is the y-axis, which is ln n, and then this axis is time. So this is like y equals to mx plus c. You see? That's the y-intercept. That's the gradient, and from there, you see, what is the half? How do you find the half-life? Well, using this equation again. Well, if half-life is, so I'm gonna let it equal to t half.
Yep.
Then if this quantity goes over here, this quantity will be half, isn't it?
Yeah.
When this time is half-life, n over n naught, whatever n in n naught is, if this is 1, this will be 2. If this is 100, then this will be 200. So this will be 1/2 here, and then e minus kt half. And you can see that from this, I can take ln and then ln again. Then I get ln half equals to, this cancel out, this one comes to the front. You get negative kt half. So therefore, the half-life is equal to natural log of half divided by minus k.
Yep.
Another way of writing this is you bring the negative sign to the top, and you get ln of half there and then k here. So this turns into ln of 2. You know, this become ln 2 because you have negative half here this negative can go to the top here, right?
And it flips.
All
Negative
right.
1, and then this flips. Half the power of negative 1 is ln2, right?
Yeah.
Yep.
So that's why this is the expression for your half-life. So if you know what the value of k is, then you just do ln2 divided by k,
Yep. Okay.
then you find the half-life. But one thing you have to be very careful is, sometimes textbook you give you this equation with a kt without the negative sign here.
Mm-hmm.
In this case, k itself
Is negative.
will be negative.
Oh, okay.
But if question gives you this one, there's already a negative sign there, right?
Mm.
So k itself will be positive. So you have to be very, very careful about this one. So in this case, this equation is based on this one here, isn't it?
Yep. Mm-hmm.
But if you're using this one and you do the same calculation, then you will find that the t half is given by ln of half k.
Yeah.
Yep.
Understand?
Yeah. Got it.
Yeah. So let's move into this. So I want you guys to. I'm just going to get some water. So I want you guys to discuss what you guys want to learn from the PPT or whatever from this.
Wait, Johnny, do you have the worksheet?
Yeah, the worksheets here.
Okay, so
Am I missing any of the worksheets?
I think you don't have. I don't think you have the number 4. Hold on.
Yeah, I've got these worksheets, and I've got this one here. So what I have is I've got these guys here.
Yep.
That's the PPT binding energy questions. All right, I'll be right back.
All right.
Yep. Oi, I just want to do half-life stuff.
Wait, no. We also have to do so what we did like recently, which is in the nuclear stability, like the value of stability and that type of shit. And also we have to do nuclear decay series. So like instead of the PowerPoint.
Yeah, we need to do that.
Nuclear decay. Like, can I cast anything?
Yeah.
How?
What do you mean task? Can't you just turn on your video?
Yeah, but like
You want to show the screen?
yeah.
Video settings. Go to video settings and you might be able to. I don't know. No, it doesn't give you the option.
No, I don't think you can.
Wait, Rav, how many worksheets have you done?
For physics,
Yeah.
none. Well, no, not none, but like 3 or 4.
Sorry?
3.
Oh, 3. Okay.
All right. Is there another worksheet?
Yes, I sent it on the chat. She said.
Brilliant. Okay. So what's this one about?
It's just like a bit of everything, I think.
Bit of everything. Okay.
Yeah, it's a bit harder.
Can we
Okay.
do like the 9-dot questions? Like the really hard one?
No, there's. Oh, could we do I didn't get hold on. Let me just check real quick. Question 38.
Do we need to go through the PPT here at all?
Not really.
No, not really.
So you guys pretty much went through it all, right?
Yeah.
Yeah.
It's just easier doing questions because then you just get
Yeah.
understand it more.
Yep. So that's this worksheet here.
Hmm.
This one here. Yeah, which question?
On the one I just sent you,
Mm-hmm.
there's question 38, 43, 31.
38.
Yeah, we'll just do 38.
Okay. So this one's a half-life of 4.5 billion years to decay according to this equation here. Uranium decaying into thorium and helium with a bit of energy there. The isotopic masses are also given here, here, here. These are all in U. If all of the energy becomes the kinetic energy of the alpha particle, what will be its energy B in millions of electron volts? Its energy is, its actual energy is 4.19. How can you account for the discrepancy? Did you guys learn relativity?
Nope.
Relativistic kinetic energy and things like that?
No, we haven't learned that yet.
Okay.
Maybe.
So maybe we shouldn't include that one here.
Yeah. All right.
So that's for, I think, year 12. So if you do 238.05077 minus 234.04358 minus 4.00260, right? Then you get this much. So that,
Wait, why do you minus them all?
minus this one, minus these two from here. That's the mass defect, isn't it?
Oh, okay. But don't you minus this one and this one plus this one?
If I do it in a bracket, then I have to plus these two.
Oh, all right. Yeah, same thing.
Yeah.
Don't you?
Yeah, same thing. I didn't just put it in a bracket. Okay, so you could have done 238.05077 minus bracket,
Yeah, I see.
Yeah.
plus 4.00260, close the bracket. Same thing. And then you times this one by 931.5, is it?
Yeah, 931.5.
Yeah, then you get 4.27. So it says that if this is the MeV, so if all of the energy becomes kinetic energy of the alpha particle, what will be its energy B in millions of electron volts? This is millions of electron volts, right?
Yeah.
Is that the answer, by the way?
You can go to the bottom and check.
Yeah, 38.
Yep.
So 4.28.
Oh, what?
Yeah, that's the same answer.
What was the kinetic? What was it talking about when it was talking about like kinetic energy and stuff? Or do we not need to do that?
Well, so if I tell you, so this is just playing with the words,
Yeah.
So there's a particle, and then this one was at rest, okay? And then 10 joules of energy went into this resting particle. And this resting and all of the 10 joules is used to move this particle.
Yeah.
What is going to be the kinetic energy of it? 10 joules. See?
Yep.
That's exactly what the question is talking about.
Oh, okay.
So yeah, it's a really, really simple question. So they say that all of the energy is used to move this particle, right? It actually said this is all useful as its kinetic energy of the alpha particle. So what will be its energy? What will be the kinetic energy?
Yeah.
Yep.
We try question 43.
Hold on. So it says that its actual energy is 4.19.
All right. Yeah.
How can you account for its discrepancy? What does it say in the answer?
It says
The daughter nucleus was carried away.
Can energy carried away by the daughter nucleus? Well, that means of course, not all of its energy will be used to accelerate the helium. It'll when these two, have a look at my hands, okay? So when they break, it'll be like this,
Yeah.
Oh yeah.
You understand?
Yeah.
So the thorium has to take a little bit of energy as well.
Oh, okay.
Wait,
Yeah,
so it's asking oh yeah, 43, it's fine.
Yeah. So 42, is it?
43.
43. Okay. So a kilogram of deuterium is combined to form a 1 kilogram of helium according to the reaction. This to this. This is.
Where'd you get that worksheet?
It's on the
Oh, really?
Yeah.
No, I didn't know.
Okay. So atomic masses are given.
Yep.
And how much energy is liberated? That's easy, right?
Yeah.
Yeah.
It's 2.0141 plus 2.0141, and then you minus 4.0026, and then you times by 931.5, and you get 23.8, stuff like that. Okay.
Wait, is that the answer? Can you?
Let's have a look. So for A, 43, 5 point blah blah blah.
Yeah. Is that?
That's in joules, right?
Oh, that's why. Yeah.
Yeah, that's right.
All right. Yeah.
So I'm
Yeah,
going to divide this by 931.5 again.
Yep. And
This is in U, right?
Mm-hmm.
so you times it by
Well,
3.0.
1 U. Yeah. Do you guys know how much 1 U is in energy?
3.0 times. Wait, I don't know.
Yeah. So I don't know either. So let's.
Oh,
look.
it's.
Wait.
I know. Okay. I think you have to convert it to kilograms and then substitute. Oh, maybe not.
They say 931.
I think you have to convert to
Yeah.
kilograms. and
Let's
then
just use this one.
Yeah.
Okay.
So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules.
Yeah. What one electron volt? Oh, we can actually use this one. We can actually use this one. This is a lot easier. If you memorize this one here, okay.
Yep. I think this is given in the
So have a
data.
look. Have a look. So this is the missing mass, right?
Yeah, it's just the mass defect, right?
That's the mass defect, and then you times this one by 931.5. Okay.
Yep.
Yeah.
And this is going to be in mega electron volts. So times this one by 10 to the power of 6. Okay. And this is going to be the EV. Understand?
So just electron. Yeah.
Just electron volts. Now times this one by this much, because 1 electron volt is worth this much, right?
Yeah.
Yep.
Times this one by 1.6 times by 10 to the power of negative 19. So that's the answer. 3 point.
I think it was 5 point something.
Yeah. Okay. So where do you think? 14 there. Do we get some same order as well? Negative 12.
Ooh.
All right.
Wait. Do we have to like what?
I think definitely.
speed of
It's
light?
1 kilogram. Sorry, 1 kilogram. Do you see?
Where?
So they were talking about 1 kilogram.
Oh yeah, 1 kilogram of
Yeah. So
Okay.
have a look. So it's 1 kilogram of deuterium, right?
Yeah.
Yep.
So this comes from. Let's write it down. So 3.815424 times by 10 to the power of minus 12 joules comes from deuterium plus deuterium becoming helium, right?
Yeah.
We've got 1 kilogram, which is 1,000 grams, is that right?
Mm.
Of deuterium. So here's what you have to do. You have to convert this into number of moles.
Yeah.
Do you know what? This is actually chemistry. You have to figure out the number of deuterium.
Yeah. No, we did this in chemistry.
Is anyone not doing chemistry here?
No. I think. Oh no, I don't think Ravine does.
Ravine doesn't do it.
I don't.
Okay, so that's fine. So deuterium is worth. If you go back to the question here, so is worth 2.0 blah blah blah, right?
Yeah.
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 So if you copy that one here, so this is deuterium 2. Blah blah blah. So have a look. 2.0141. That's U, right? But we're going to times this one by 1.67377 times by 10 to the power of negative 27.
Is this to convert it back into kilograms?
Yeah. So this is how much each deuterium weighs in kilogram.
Okay. Yeah.
But how do you do that?
Kilogram.
So you just did 2
I
point.
just this one times by this one here because
Oh, okay,
one
yeah.
here is worth this much.
Okay.
So I times this one by this much.
So that's
Okay.
how much one kilogram of deuterium weighs.
No. 1 deuterium weighs in kilogram.
Oh yeah. Okay. Yeah.
Mm-hmm.
Yeah.
Yep.
So instead of converting to gram, so you got 1 kilogram of deuterium. So how many deuteriums are there? You have to divide 1 kilogram by this one here.
Yeah.
1 kilogram divided by the answer. Oops. Then you get this many deuteriums.
Mhm.
So what do we do next, guys? We get this much energy from each reaction.
Okay.
I want you guys to think.
Yeah.
So
Okay, I'll summarize what we have done so far.
yeah.
Yep.
We add these two and then minus this one. So we get the
Mass defect.
mass defect and then times that by 931.5. And we
Yeah.
get the energy
Yep.
in mega electron volt, and we times that by 1 million to get the energy in electron volt, and then times that by 1.6 times by 10 to the power of negative 19 joules to get the energy in joules.
Yeah. But
Okay.
So this is the energy that comes out from each reaction.
yeah.
Okay.
And now we have 1 kilogram and 1 kilogram of deuterium. So we
Yep.
converted 2.0141 U into kilogram by multiplying this one by this one.
Yep.
And then that's the mass of each deuterium. And we divide 1 kilogram by the mass of each deuterium to figure out how many deuteriums there are.
Yep. So
Well, the answer is you have to times this one. We need to figure out the total energy that comes out from reacting 1 kilogram of deuterium. You see? So you have to multiply this quantity by the number of reactions. But this is number of deuteriums.
So it's the number of particles.
Number of deuteriums.
Yeah.
I'll give you another clue. 2 deuteriums compose 1 reaction.
So do you multiply by 2?
You divide this quantity by 2.
By
Oh,
2.
divided by 2.
So that was the number of deuteriums. This is the number of the reactions, right?
Yeah.
So you times this one by 3.8154424 times by 10 to the power of negative 12.
Yeah.
Then you get the answer.
Okay, yeah. I see.
So
Yeah.
yeah, 5.75, 5.65.
Yeah, it's probably just used like rounding or something.
Yeah, it could be a little bit of rounding error.
Yeah.
Doesn't matter. I think this is acceptable.
Yeah, it's good enough.
Yeah.
Wait,
So yeah, this video, this is all recorded. So if you guys want to go back to it, I can send it to you guys. Okay.
Okay, yeah.
Yeah.
Okay.
Yeah.
What about part B?
No, let's do part B now.
Yep.
So we are seeing 5.6. We'll assume that 5.75 times by 10 to the power 14. Okay. This is joules of energy that comes out from the reaction from 1 kilogram of deuterium. Now let's go back. Is Vishal here as well?
Yeah.
Yeah, he's been pretty quiet. All right. What was the question again?
It was I think some like chemistry you have to do.
Yeah, if confined helium has a specific heat capacity of 3.13 A, so this is a Q equals MC delta T stuff, right?
Yeah.
Yeah.
By how much does the temperature increase as this energy is added to it? Wow. But how many heliums are there though?
Is it 1 kilogram? I don't know.
Yeah, it's a bit difficult one. So you have to make a bit of assumptions. Okay.
Assumptions, yeah.
So it says if the confined helium has a specific heat of that, well, we were trying to figure out by how much. So Q equal to MC delta T. We're trying to figure out delta T, right?
Yeah.
Yeah.
So Q
So
over
then
MC. So Q is equal to 5.75 times by 10 to the power 14 joules.
Yeah.
Yeah.
Well, that's a lot of energy compared to this one. And mass of helium, that's what we have to figure out. C is 3.138.
So do we just do number of moles is equal to mass over the mole mass?
So we have to figure out how many heliums there are, right?
Yeah. Wait.
So you got 1 kilogram of deuterium. Okay, what do we have to do to figure out the number of the heliums?
Oh, can't you just convert the U of helium to
Well, the number of helium would be the same as number of reactions, right?
Wait, why can't you just convert 4.0026 into kilograms?
But you have to know how many heliums are there as well. So 4.0026 times by the
931 point.
yeah, this one here, 1.67377 times by 10 to the power of 27. That would be that would be the mass of 1 helium, isn't it?
Yeah, mass of 1 helium.
Mass of 1 helium.
We don't know how many there are.
Yeah.
We need to figure out. So you see, gram has to go into this quantity, right? Because you see this unit here, 3.138 joules per gram.
Per gram. So grams.
So gram has to go in here. But this is mass of 1. This is in kilogram, and this is mass of only 1 helium.
Okay. So, yep. So doing like times about 4 or something.
Okay. So you see how we did this one? We look over here.
Wait, so you just times it by the number of reactions?
Number of reactions. If you figure out the number of reactions, then you can figure out the number of the helium. That's how many heliums will be formed.
Yeah.
Number of reactions will be the same number of heliums. So how do we figure out the number of reactions? Remember? We just did it just above, you know?
Was it?
So you figure out how many deuteriums there are, right?
Yeah.
Times by this one, 67377 times by. That's the mass of each deuterium in kilograms, and you divide 1 by what the hell?
Wait, why do you divide it by 1? Why do you do 1 divided by that again? Oh,
because there's 1 kilogram of deuterium, and you figured out this answer here is the mass of each deuterium in kilogram. So 1 kilogram divided by, you see, if you have 10 kilogram of orange and each orange weighs 1 kilogram, then what do? You divide, right?
Okay, I see. So that means, okay, good.
That means the number of oranges.
Yeah.
So you got 1 kilogram of deuterium, and each deuterium weighs about, whatever that was. So we divide, and this is the number of deuterium. And we divide this one by 2 to figure out the number of reactions, right? So this is how many helium there are.
Oh, and then you just multiply it by...
you multiply this one, multiply this one by 4.0026 times by 10 to the 1.67 again, 67377. So this is the mass of each helium, right?
I just need to take a quick toilet break. I'll be back in a bit.
Yeah.
That's right. So you get, it's almost 1 kilogram, you see?
Yeah.
It's almost, Yeah, because you got 1 kilogram of deuterium, and then that turned into 1 kilogram of helium. So nothing much is lost, right?
Right. So can you just assume that from the start, or do you actually have to?
So if you times this one by 1,000, then you get 993 grams. So, but there is actually an easier way of figuring out this mass here.
Yeah.
So, and it kind of makes sense, right? Because you started with a 1 kilogram of deuterium. This turned into 0.99364 kilograms of helium. Is that right?
Yeah.
So we figured out this quantity through this complicated process. We took sort of a detour, but there's a quicker way to get there. Have a look. If you simply divide this one 4.0026 and then 2.0141 plus 2.0141.
Oh, that's shit.
That's you see, this is the percentage. This is the ratio of that one over that one. And then you have to times this one by 1. So you get the same thing here.
And then if it was like 2 kilograms, you times it by 2.
Yeah. So for example, so the idea is if I had 3 kilogram plus 3 kilogram and that became 5 kilogram, 6 kilogram became 5 kilogram, and I have 1,000 kilogram of this, the 3 become 5. But if I have 1,000, then how much does it become? You have to times 1,000
by the percentage of
by the percentage 5 over 6, right?
Yeah, and
that gives you the answer easily. 833.3. So that's the kind of idea here. So you can easily work that out from there. Okay.
Okay, and then if you just sub into
you sub in 993.644 because this has to be in grams.
Yeah.
993.644. So I think the temperature will rise by like several million degrees or something. It's going to be too much energy liberated. And if that goes on to, you see, if through this fusion, this is what happens on the sun. Deuterium combines to become helium and energy is liberated. That comes to us, right? To the earth.
Yeah.
To the space. But if all of that energy were to be concentrated onto this helium, then of course the helium will rise to by several million degrees or something, right?
Yeah.
And that doesn't really happen.
Yeah,
so this is 5.75 times by 10 to the power of 14 divided by 993.644 grams times by 3.138 here. Then you get this much.
Yeah, that's the right answer.
This much degree.
Yeah. 3. Yep.
Yeah, that's right.
Okay. Yeah. Will or Vish, Ravin, do you guys want to do any other question?
Just curious that.
So those are a Will's question, but Ravin and Vish, do you guys want to go through any other thing?
I want to go through question 56 on that worksheet.
On the same thing?
Yeah.
56 is it?
Yeah.
This one here?
Yeah.
Okay. So this one's about decay, right?
Yeah.
Yeah.
Sample contains N1 nuclei with decay constant of lambda. Is that is that K?
Yeah.
No,
lambda's the same as K.
Yeah.
Same as K. N2 nuclei with decay constant at lambda 2. What is the total decay constant for the sample in terms of total decay constant? Okay. So N1. So what is the situation? Let's have a look at the answer first. 56 is like that. Did you see anything like this in the lecture note? Combined?
No.
No.
Was this one of the assigned questions?
Yeah, this is pretty much like what every single question in the worksheet. It's assigned.
Okay. Let's come back to this one later. I don't really understand the question.
Yeah.
I can give the answer to you later, maybe.
Okay.
I can do some research on my own time.
Yep.
Will, did you have any other question?
I couldn't do. Hold on.
Can you do question
Yeah.
47?
47.
Yep. Is that
Okay.
okay?
Yep, 47 here.
Wait, Vish, have you tried the 9 dot ones? All of them?
Oh no, I'm just doing some now.
Oh, well,
They're really hard.
try them first.
No, I don't even understand the question. So, what's the point?
Okay, so half-life of a cobalt-60 radioactive element used in the reactor used medical commercial radiation. What's this one? 1.33 and 1.17 MeV gamma rays. What does it mean by that? 1.33 and 1.17?
I don't know.
Does it mean... Oh, okay. So for medical case, I think it's emitting this much radiation, and for commercial, I think it's emitting this much radiation, gamma rays.
Yeah.
Anyway, so it has got the half-life of 5.3 years. How many atoms of a CO are there in 1 milligram of the material? And what is the decay constant for the material? How many distinctly occur in... Okay, so that looks pretty easy. So 1 milligram of the material. So 1 milligram is the same thing as 0.0001, right? 0.0001, is it?
Yeah.
Yeah. So 1 milligram is same as 0.001 kilogram. Mm-hmm.
Yeah.
Yeah.
And then let's have a look at the mass of cobalt-60. Cobalt-60 is... It gives two types of gamma rays like that. So I'm just going to paste this one. Hello?
Yep.
So we're going to look at the first question. How many atoms of this are in one? That's easy, right?
Yeah. So you just.
What do you have to do?
Can't you just use the moles equation and then times by Avogadro's number or whatever?
I think there is an easier way. You times this one by. You times this one by the 1.67 times by 10 to the power of negative 27. And get a kilogram and divide this one by that, right?
Wait, isn't it already in kilograms?
So 59.9338222, that's in U, times that by. We know this constant here, 1U, this one here.
Yeah.
So 1U is that much, so it's a 1.67377 times by 10 to the power of negative 27 here, right?
Yeah.
Therefore, this is the mass of 1 cobalt in kilograms. Divide this with 0.001 by the answer.
Wouldn't it be the other way around?
No.
Okay.
This is how much there are, and that was how much it weighs each. So you divide it by this one. You just have to get used to it. Yeah, it's a little bit confusing, you know. Sometimes people flip them around.
So is that how many atoms there are?
I think so. Do you want to check the answer?
Yeah, sure.
47?
1.0 times 10 to the
19 atoms. So I think, okay. So if you round it up, then you should get 20. for this one. Why is it 19? Maybe we made a mistake. I don't know. So this calculator is giving us 9 point. Maybe we missed
A decimal.
a decimal. Is it supposed to be 0.0001?
Could be, yeah.
Wait,
So 1 milligram is the same as 1 times 10 to the power minus 3, isn't it?
It's 0001.
Yeah, it is 0001. So 0.0001?
Yeah, 3 zeros.
Are you sure?
Yeah, I'm fairly sure. Because 1 milligram is equal to 10 grams, right? Is equal to 0.1 gram, right?
All right. 1 kilogram, 1 centigram, 1 milligram. 1 milligram should be 0.001. Oh, it has. Oh, that's right. It's actually this. Sorry, I messed up. So 1 milligram is this much grams. Sorry,
All right.
not kilogram.
Oh.
Right? Yeah, gram is the center of everything.
Mhm.
And then you divide this one by 1,000 again. Then you get this in kilogram, right? So it'll be 0.00 and then 3 more zeros. 3 zeros and a 1. That'll be the kilogram, okay?
Mhm.
Jeez. Okay.
That would be the...
Oh, and then if you divide it by that, you get the right answer. Times 10 to the...
Yeah. Oh, but I'm still a little bit doubtful. Hold on.
Okay.
So you got this one here, 59.9338222 times by 1.67...
Times 10 to the negative 27.
377 times 10 to the power of negative 27.
Yep.
This is in kilogram, right? Of each cobalt.
Yep.
And then you divide 0.000001 by the answer.
And so.
Then you get this. Oh yeah, there you go.
And then if
So
you round up,
yeah, that's right.
you get...
So 9.96 times by 10 to the power of 18, right? So here's a trick. You can round it up to 10.
By. Oh,
Then you get this. Then you get this one.
Yeah. Okay.
Okay.
Oh, but I think it's to the power of...
It's power of 19 in the answer.
All right, yeah. Don't worry.
Yeah. There you go. So I want you to think about the other part. What is the decay constant for the material? I just need to go to the bathroom quickly.
Yeah.
So you guys can try this. Vishal and Raveen, have you guys worked this one out?
No.
No? Okay.
No.
So you can try this.
What is the decay constant? Rav,
Yeah.
how are you, bro?
No, I'm alright. How are you?
You were so pissed yesterday.
No, it was just so annoying. I have a lot of stuff to do.
Sounds bro. You okay?
Yeah.
Okay.
Yeah, I'm fine. I'm just busy. After this, I want to try question 37. From the
Which question?
37. It's on the PowerPoint actually. I don't have that worksheet. It's not on my OneNote.
37.
Yeah. Could you just
On
check?
this worksheet or...
Yeah, just check if you have it. Just check those. Because there's there's a bit of it from the PowerPoint. I think you just like screenshot it or something.
Wait, where? What question?
Question 37.
On.
Ooh.
Whose window is that?
All right, so it says half-life is 5.3 years, right?
Yeah. Do we have to convert that to seconds?
It doesn't matter.
Because
But I think it says in the end how many integrations occur in each second. So I think it's better to convert that into seconds. I think, yeah. And you have to decide whether you're going to use. Is it usually with a negative sign, guys?
Yeah.
It is.
For your cases, okay. So you just have to do ln2 divided by k. K is equal to ln2 divided by half-life, isn't it?
Yeah. Same.
So K is equal to ln2 divided by t half, isn't it?
Yeah.
So this will be 5.3 times by 365.25.
Okay.
Or we can do 365. The reason why I put 25 there is because there's a leap year.
All right.
When there was a leap year, there's one more day.
Yeah.
So if you take the average of a 365 and 365, 365 and 366, that's 365.25, isn't it?
Yeah.
And then that's how many days there are. 24 hours times by 60 times by 60, right?
Yeah.
Then you get that many seconds. So ln2 divided by the n. So then you get that as your k.
Yeah, that's what I got.
4.144 times by 10 to the power minus 9.
Yeah.
That's the k there. Now, so let's talk about this one here. How many integrations occur in each second in 1 milligram of the material? Did you guys get an equation that allows you to do something like this one?
Not sure.
Is it
Right.
wouldn't it just be A is equal to A times e to the negative lambda t?
Sorry?
Isn't it the same as the, what's it called, the other exponential one, but just for activity?
I'll just do it in my way. Maybe you guys were given some special formula, I'm not sure. So you've got the dn dt, that's the rate of decay. Maybe this is in the lecture notes. Your lecture note here says, right here, so you guys were given this stuff. These are the lambda, the constant k, right?
Yeah.
But at the start of it, you were given this one. So dn dt is given by negative lambda n. So have you guys been doing differentiation and things like that at school in specialist maths? So what does dn dt mean? This means the rate of change of n. Is that right?
Yeah. With respect
Let me just give you a little bit of back. Everything starts from here. So for example, our Canberra population, it increases, right? But the number of births, number of people being born every day depends on the population of the Canberra of
Yeah,
Canberra.
yeah.
So d and dt is proportional to the number of the number. So if this number is large, then in this case it's negative, so it's going to decay. So the more you have, the more you will decay. But if it's like dp dt is equal to some constant k and then population, then this population, the rate of change of the population will depend on the population itself.
Yep.
And then if you integrate this one, do you guys have you guys been doing anti-differentiation as well?
Yeah, a little bit.
A little bit. So I'll show you a little bit here. So this is a little bit of digression, but if you do d and dt equals to negative lambda n, you separate the dn with dt, so dt goes here, and then you put integral sign like this. An integration of 1 dn is just n, right? Because integration of 1 dx is just x. I'm not sure if you guys were doing this. I'm just going to do this quickly. And this one is just, hold on. This n has to go. I think I messed up. So this n has to go over here. So it has to be 1 on n. And there's a lambda. You have to completely separate the variable. Integration of 1 on n dn is ln n, and integration of this is constant, so it's lambda t. And then if you take the e both sides, then you get plus c, by the way.
Yeah.
And then if you take e here, then you get e and ln cancel out, you get n, and then this is e to the power of negative lambda t times by e to the power of c, and this is the constant, which is the same as the n naught. So that becomes n naught e minus lambda t in here. So that's how you get this equation. It all comes from this one here, right?
Yeah.
So this is done through integration. Now,
Okay.
we have got the k value. We know that d and dt, so this is the rate of decay, is equal to negative lambda of the n.
Yep.
So, have a look. This is a negative 4.144 times by 10 to the power of minus 9.
Yep.
And the current mass is 1 milligram, isn't it?
Yep.
But 1 milligram is the same as this quantity here. So I'm going to put that in here.
So do you just multiply that by what the answer we got before?
Yeah, multiply this one by 0.000001.
Yep.
Then this will be negative 4.144 times by 10 to the power of minus 15. And you know what the unit is? This is kilograms per second. Because this was in kilogram, right? And this is in seconds, right? This is the kilogram.
Yeah.
So what you're getting is you're losing as many kilograms every second. You're losing.
Is that the same as BQ or whatever?
BQ becquerel.
Yeah.
What's the unit of becquerel? I forgot.
Yeah. I think it's disintegration.
Yeah. So it's not yet.
Yeah.
It's not yet becquerel. So we're looking for becquerel here. We got this many loss in mass per second. So we have to convert this into number of integration. Understand?
Wait. So why can't you just times 4.144 times 10 to the negative 9 times that by 1.1 times 10 to the 9?
Yeah. We can do that as well. Where was that number?
The one we just got. So how many atoms?
Yeah, how many atoms were there?
1 times 10 to 19 on top of the white.
Oh yeah, this was the number of the how many atoms there are. Yeah, that's right.
Yeah. 1 times.
So yeah, we can actually plug that in here as well. Then we get the becquerel exactly.
Yeah.
So yeah. Anyway, I just wanted to show you the different perspective.
Oh, okay.
If you put this number in, okay, then you get how many kilograms you're losing per second. if you put this number in, let's have a look. That's 4.144 times by 10 to the power of negative 19, or negative 9, sorry. And then times by 1 times by 10 to the power of 19. So this is how many atoms there are, right? How many couples there are. So this will be negative this much atoms per second, right? So this is the unit for this one is atoms.
Yeah.
Yep.
Yeah, so if you check the answer, is that right?
Yeah.
Yeah, 4.14. What was this one?
That's the number of I don't know.
That's the decay constant, was it?
Yeah, that's decay constant. Yeah.
Yeah, decay constant. This one here,
Yep.
and you got this one here.
Yep.
That's
Wait, so
that's
is the
macro.
so basically is the equation n is equal to NO times lambda?
Oh, so the rate of decay.
Yeah.
Or this can be known as number of decays
Yeah.
per
So-
second
So dn dt.
would be negative lambda, and this lambda has to be in seconds, okay?
Yeah.
Because this is in seconds here, times by the current number. This is not n naught. This is whatever number you currently have.
Mm.
Okay, so this is the current population.
Okay.
You know, because the rate
But if you
changes
do-
all the time. Rate,
If you do,
yeah.
If you do negative lambda, why do you get a negative answer?
If I put a negative what?
Oh, I put negative
Mm-hmm.
4.14
Yeah.
whatever, and then I got the answer was negative. It's like still the same answer, but it's just negative.
So our lambda here was not negative, right?
Yeah.
So that's why we have to put a negative there, because it's decay.
Mm.
So in my calculator, I didn't put negative sign.
Yeah. Why not?
Oh, why? Well, because I can just put negative later. That was just a bit lazy, you know. But I put it in the end like this, you know.
All right. Yeah.
Yeah.
I thought the answer was positive.
So the equation says there must be negative.
Yeah.
So here's the thing. The question is saying how many disintegrations occur, right? So they only want positive answer.
Oh, I get it now. So that's how much like your.
But if they were saying, what is the rate of decay when there is 1 milligram of the material, then because rate is either positive or negative,
Yeah.
then in the answer you want to include the negative sign.
Oh, okay. I see. Yeah. Okay.
So depending on, you know, so for example, when they ask you what is the speed is always positive quantity, isn't it?
Yeah, but if it's velocity.
It's a lot. So depending on how the question is given, you may have to give negative answer, positive answer. But even if you give negative answer, I don't think it'll really matter. Your teacher will give you full mark.
Yeah.
See? Yeah. Yep. All right, we'll call it a day. I want you guys to send me questions that you guys want to study. Maybe I can spend some time and give you guys written solution.
Yeah.
All right. So make sure you guys decide time and date yourself and make a booking through the online booking sheet. You guys can do that through Vish, Michelle, or Raveen, or you got one person has to do it.
Okay.
Yep.
And like today, like during today's lesson, you guys sent me this file, right? Will sent it to me.
Yeah.
But everything, if it's online tuition, everything, or even for face-to-face tuition as well, everything has to be sent to me before tuition, and you have to tell me, like, I would like to study this question, I would like to study that question, so I can prepare, you know?
Yeah. Okay.
Because, you know, every school is different, and all the questions are different, so I really have to need some time to prepare, okay?
Yeah.
So today I didn't have any time to prepare. For example, like this question, I have no idea at the moment. But if I look at it, maybe do some research, maybe I can figure it out, okay?
Yeah. Okay.
But I'll have a look at this. Also, send me some other questions that you like to study. Okay.
Okay.
Yeah.
Yes.
All right. See you
Thank
guys.
you.
All right. See ya. Thanks,
Yeah.
Johnny.
Okay.